Chapter 12, Chemical Equilibrium. So, table of contents, 12.1, the equilibrium condition. That's your basic starting point. Chapter 12.2, the equilibrium constant. We're going to see a lot of this coming up. 12.3, equilibrium expressions involving pressures. It's variation on what we're going to see on 1 and 12.2. 12.4, heterogeneous equilibria. 12.5, applications of the equilibrium constant. How can you do something useful with the stuff you learned in 12.2 and 12.3? 12.6, solving equilibrium problems. Going to do a lot of that. I guarantee that's going to show up on a test. And 12.7, Le Chatelier's principle, also going to be on your test. So let's go on. We're going to start off with 12.1. Let's look at our overview. Our last chapter, we talked about kinetics. We looked at reaction rates. Right? So we had that little k that was our rate constant k. We looked at our different rate laws, and we saw how concentration, temperature, and catalyst affect how fast a reaction will go. This chapter in equilibria is about the extent of reactions. We're going to look at two numbers, Q and K. It's a big K this time, not a little k. Those two Ks are, as we're going to see, related. We're going to look at the effects of concentration, temperature, and catalysts on equilibria. So, why would we want to study equilibria? Well, human physiology involves equilibrium. So oxygen concentration in your blood and tissues are in a state of equilibrium. So you've got hemoglobin and oxygen that transforms into oxyhemoglobin. Altitude sickness is caused by a reduction of oxyhemoglobin concentration in blood and results in headache, nausea, fatigue. The pH of blood is maintained at 4.7 due to an equilibrium involving carbon dioxide, where carbon dioxide is dissolved in water and it's going to form hydrogen carbonate and carbonic acid. So as one exercises, more CO2 is produced, making the blood more acidic. Your lungs are equipped with a mechanism that encourages the production of carbonic acid that helps neutralize the acidic condition in the blood. So all this stuff about buying alkaline water at 8.8 pH or what have you is just a load of nonsense. Your body spends a great deal of effort to keep your blood pH and your physiological pH within a very narrow range. Drinking some mildly basic water isn't going to do anything to it. If you're outside of that physiological pH range, you've got a severe problem and you're probably going to be dead. As we will see, your body also spends a lot of energy to stay out of equilibrium. So there are some processes you want to be in equilibrium, other processes that we're going to constantly fight to stay out of equilibrium by using energy to input into that and keep us out of equilibrium. So kinetics is the speed of a reaction. How fast does it happen? How many molar per second? We're looking at the concentration of a product as it appears or of a reactant as it disappears per unit time. Equilibrium, on the other hand, applies to the extent of a reaction, the concentration of a product that has appeared after an unlimited time or once no further changes occur. So in our equilibrium processes, these are often dynamic equilibrium processes, just like we saw with water vapor or vapor pressure above a liquid that was in a dynamic equilibrium, where sometimes a given molecule might have been in the gas phase or it might have been in the liquid phase, but the total number of molecules in the liquid and gas phases were constant. So at equilibrium, here is our connection. Our forward rate of reaction and our reverse rate of reaction are equal to each other. And that's our tie-in to kinetics. Right? So equilibrium is going to shift as kinetic shifts. So we're going to see some of these equilibrium conditions be very temperature dependent, just like we saw how our values for K, little k, were going to be temperature dependent. And so we'll tie that back into our energy. So this is, again, related to the energy. This class all about energy. So our system is in dynamic equilibrium on the molecular level when no further net change is observable because the changes in one direction are balanced out by the changes in the other. So here is a great example of that. So our value K, and we're going to use a big K now, is going to be equal to our forward reaction rate and our backwards reaction rate. And if our overall rate law is our rate constant K times the concentration of A to the M and B to the N. Well, our reaction orders aren't going to change for the forward and reverse reaction. So if we divide that, those guys cancel out. What will change is our K value. So we can think of this as our K forward over our K reverse. And if you've got a mall, right, and let's say there's 50 people on the top and 50 people on the bottom, right? As some people are going up the escalator, some people are going down the escalator. The total number of people on the top and the bottom are the same, but they may not be the same people. We've got a rate of forward reaction going up to the top and a rate of reverse reaction going down, and they're equal to each other. So our total numbers on the top and the bottom are going to be the same. If we were to draw this out on a graph, like in Chapter 11, Chapter 11 was very much interested in these curvy parts. What was our concentration as a function of time? Right? How much of our HI did we have at 100 seconds? How fast was this going? How strongly dependent was our rate on the concentration of I? Was it first order? Was it second order? And we looked at the relative rates. Right? What was our stoichiometry and how did that play into the appearance of HI versus the disappearance of I2 and H2? Since the Chapter 11 happened on the left-hand side of that. If we let things go for a really, really long time, right, our reactions are going to slow down, and we're going to reach this equilibrium condition, this dynamic equilibrium, where we've got a steady concentration, an unchanging concentration of our reactants and products. So our reaction has basically finished happening. There's still molecules moving around. It's still undergoing a little bit of forward reaction, a little bit of reverse reaction, but it's stable in terms of the concentration. Our concentrations no longer change. So our definition is that a state where the concentration of all the reactants and products remain constant with respect to time. So when a reaction starts, the reactants are consumed and the products are made. The reactant concentrations decrease and the product concentrations increase. As reactant concentrations decrease, the forward reaction rate is going to slow down. Right? And conversely, the reverse reaction rate, because we're looking at that from the opposite point of view, a reverse reaction rate, because we got more reactant or we got more products, is going to move back towards the product. A reverse reactant rate is going to speed up because the concentration of the products has increased. Eventually, the products can react to reform some of the reactants, assuming that the products are not allowed to escape. As product concentration increases, the reverse reaction rate is going to increase. Remember, we saw equilibrium happen with vapor pressure. The total number of gas phase molecules above a liquid was constant at a given temperature. The processes that proceed in both forward and reverse directions are said to be reversible. And so now you're going to start seeing this new double-sided arrow that indicates my reaction can go in a forward direction and in a reverse direction. Chemists commonly use two kinds of arrows to indicate the degree of completion of the reaction. We've got a single arrow that all the reactant molecules are converted to product molecules at the end, and we got the double arrow, which indicates that the reaction stops only when some of the reactant molecules have been converted into products. So these guys here, those are going to be our equilibrium states. This is going to represent something that goes vastly towards one direction in forming products, or it might be an irreversible reaction. So if we look at the changes with time and the rates of forward and reverse reactions, our forward reaction rate is going to go down. So this is going to be K times our concentrations raised to whatever power they are. And our reverse rate is going to increase. And at some point, those two rates are going to equal each other. And then we're going to be at our equilibrium condition. If we look at our concentration as a function of time, our concentration of our product is going to increase, and the concentration of the reactants are going to decrease over time, and then they're going to reach this steady state where we're not going to observe a change in their concentration. Our equilibrium position of a reaction, left, right, or in between, is determined by the following factors. Initial concentrations, right? How much stuff did you start off with? The relative energies of the reactants and the products, and the relative degree of organization of the reactants and the products. The concentrations of the reactants and the products of a given chemical reaction remain unchanged when mixed because of the following reasons. The system is at chemical equilibrium. The forward and reverse reactions are so slow that the system moves towards equilibrium at a rate that cannot be detected. So this is what's happening with your diamond. It's just that the reaction rate is really, really, really slow and we can't see it. Right? Sometimes there is going to be movement towards reactants or back towards products or back towards reactants, but we may not be able to observe it